Example 1 here on conditional probability and tree diagrams is taking a look at tree diagrams. So here Sally has a bag of sweets, there's 12 blue sweets and 18 red sweets in total. Now if Sally takes 2 sweets without replacement, we want to calculate the probability that she takes exactly 1 blue sweet. So here, what I'm going to do here now is use a tree diagram to represent this. So in this case, don't forget we just have simply red and blue sweets. So here, if I represent red sweets here with this top branch, and blue sweets with this bottom branch here. So this is for blue sweets, and this is for red. Okay, so here first, if there's 18 red sweets, and there's a total of 30 sweets in total, that's going to be 18 over 30. Okay, and in that case, this means blue here is 12 over 30. Now here, if Sally takes a red sweet first, in that case we have another 2 branches here. Well, if she's already took a red sweet here, and remember, this is without replacement, in that case then, there's going to be 17 out of 29 here, okay? There's 1 less sweet in total, and we took one of the red ones here. So in that case, that would be for red sweets, and again, blue here at the bottom. And in that case, this would be 12 over 29. And then finally, let's do the same here. If we take a blue sweet first, again, we'll have another 2 branches with red being the top branch, and blue being the bottom branch. And again here, remember, we're doing this without replacement, so here this is going to be 18 over 29, because we didn't take a red sweet, we took a blue sweet, so we've got 1 less sweet in total, so that means this is 11 over 29. Okay, so that's our probability tree, or our tree diagram here. Okay, so now we're looking for the probability that she takes exactly 1 blue sweet. So in that case, there's 2 possible ways we obtain exactly 1 blue sweet here. So the 2 ways we obtain this is by starting here and taking a red sweet first, and then obtaining a blue sweet on our second chance here. Okay, so that would give us exactly 1 blue sweet there. So that would be the probability of getting red and blue. Okay, so that's the probability of red and blue here. And in that case here, that's going to be 18 over 30. That's 18 over 30 times by 12 over 29. Okay, if we calculate that here, that simply gives us 36 over 145. And then the other possible outcome here is by taking a blue sweet first, and then a red sweet here. Okay, so that's the probability of getting a blue and red. And notice here, this would give us the exact same multiplication here. This is going to be 12 over 30 times 18 over 29. So that's 12 over 30 times 18 over 29. So it won't give us the exact same calculation here. However, the final outcome would simply be 36 over 145 again. Okay. So simply, if we want the probability of 1 blue sweet, so therefore the probability, and again, let's just go back to our original pen colour here, probability of 1 blue sweet, that's simply going to be the sum of these 2 individual probabilities. So that's 2 lots of 36 over 145, and that would give us 72 over 145 there. Okay, so that gives us the solution to example 1 there. Moving on to example 2 now, which is taking a look at conditional probability. So here there's quite a bit of context to this question, so I'll take a moment just to kind of read over this question, and we'll take a look at this now. So here, what we're looking for is a probability that he had breakfast. So if we see Jonathan outside of his house, what is the probability that he had breakfast? So here we're using conditional probability here. So what we're looking to find, so we're looking for the probability of having breakfast, so that's probability of B, given that he's left the house. So the probability of B given L here. Okay, so that's what we're looking to find. So to do this here, what we're simply going to do is use the formula for conditional probability. Now before we do that, let's just note a few things that we're going to need in that formula. So the first thing we need here is the probability of breakfast, which we're told is 0.3. So the probability of B is 0.3. And we're also going to need the probability of B complement, so the probability that it doesn't have breakfast here. which we can denote as B complement. Okay, so that's going to be 1 minus 0.3, giving us 0.7 there. Okay, what we also need here is the probability that he's left, given that he's had a breakfast here, which we can find in the question. That if he eats breakfast here, the probability that he leaves the house is 0.6. So that's 0.6 there. It's 0.6. And finally here, the probability that he leaves the house, given that he doesn't eat breakfast here, and that will simply be 0.2 here. So he does not eat breakfast, but he leaves the house. That's 0.2. Okay. So using all this information then, we can simply find the probability of B given L. For this probability here, using our formula, this is simply going to be the probability of L given B here, times by the probability of B, and this is all divided by probability of L given B, times by the probability of B again, plus the probability of L given B complement, times by the probability of B complement. Okay. So here, putting everything that we've got here on the right hand side that we need appropriately into the formula here, what we obtain is 0.6 times 0.3, and this is all divided by 0.6 times 0.3 again, plus 0.2 times 0.7. Okay, and if we simply calculate this here, what we obtain is 0.18 divided by 0.32, which we could express here as 9 over 16, and 9 over 16 we can express as 0.5625 there. Okay, so that gives us the required probability there, and that gives us the solution to example 2 there.